Science on Surfaces.
So welcome to this podcast. Today we will talk about interfacial rheology and how that can be used to predict emulsion and foam stability. So here with me in this call I have my colleague Susanna Lauren, who's an expert on interfacial rheology and surface-related phenomena. And she's been working at Biolin Scientific for around 8 years on these topics. And before that, she did her Ph.D. on microfluidics and superhydrophobic surfaces. Hi, Susanna.
Hi, nice to be here.
Yeah, so I'm really looking forward to learn all about interfacial rheology today. And if we just start with the basics. So rheology, of course, I've heard of, but interfacial rheology, are they related?
Well, not really. I mean, we are using the same words, so it's basically the similar terminology we are using, so such as viscosity, and both of them are actually studying the flow properties. But if we think about the traditional, like bulk rheology, we are looking at the flow properties of the bulk. And then when we are talking about interfacial rheology, we are actually interested in the flow properties of the interfaces.
So you said flow properties and you also mentioned viscosity. So if we could just define or describe viscosity, which I guess is like a key.
Yeah, it is. Yeah.
Key concept.
So, yeah, absolutely. So if we think about, we can think about first bulk viscosity. So that's the property that kind of arises from the frictional forces that are present in layers of fluid when they are in relative motion. And so maybe it's easier to understand if you think of like a narrow tube and you push liquid through that tube. The liquid is moving more or faster at the center of the tube than on the edges. And you need some kind of a stress, for example, a pressure difference that you can force the liquid to go through the tube. And the strength of this force that is needed is related to the viscosity. So if you consider, let's say, water, it's relatively easy to push that through a tube. But then take honey, for example, you can understand that you need much more force to be able to do that. So then the viscosity of the honey is higher than the viscosity of water.
And that of toothpaste would be even higher.
Yeah, exactly.
Yeah. Okay, so we talked about viscosity, and that is like a bulk property, but we're talking about interfaces, like interfacial rheology. So how does this relate to interfaces, and what is an interface?
Yeah, so I mean, it's not just any type of interface, of course. So when we are talking about interfacial rheology, we are actually studying the interface that is stabilized by some kind of a surface active molecule. So surface active molecules, we have hydrophobic and hydrophilic parts. And if you put those molecules in air, water, or oil water interface, they will align and arrange so that the hydrophilic part is in water and hydrophobic part is in air or oil.
So what do you mean by stabilize?
So maybe we should now consider a little bit already what is an emulsion, basically. So emulsion is something, is basically a dispersed system where we have a let's say oil drops in water. So then we have oil in water emulsion. And I mean, if you mix oil and water together, they will eventually just separate into oil phase and water phase. So you actually need that third component, which is the surface active molecule, so that you can actually make it a dispersed system. Otherwise, you will just have oil and water on top of each other. But if you add that surface active molecule, you can actually form a dispersed system where you have oil droplets in water.
Okay, so mixing one phase with the other. But so this is, you talked about emulsions now, but then what about foams?
So foams, you can maybe consider them as air-water emulsions in a sense. So instead of having oil as the other component, then you have air. So then in the same way, you need some kind of a surface active molecule to stabilize that kind of a system so that you can get those air bubbles, for example, in water.
Okay, so it's a phase mixing in both
exactly.
cases, you could say. Okay, so I still don't quite get how these surface active molecules stabilize the interface. I mean, how does that work?
Yeah, I mean, it actually works in two ways. So there is let's think about this example where we have, if you just have water on a piece of a beaker, let's say in a beaker, and then you put oil on top. So then you have two very separate phases. Then you try to mix those two together without any kind of surface active molecules present. You might see, let's say, little droplets forming in water, but it doesn't take that long when the oil actually just separates from water and you can start to see these two separate phases again. And the reason for this is that the interfacial tension between the oil and water is quite high. So there is actually, I mean, from thermodynamic point of view, we are increasing the total energy of the system because we are increasing the interfacial area between the water and oil. I mean, if you have a tiny oil droplet in water, you will have a huge surface area contact in between. So we need to have these surface active molecules to decrease that kind of total energy of the system. So that's one aspect of it. And the other thing is that if we think about if you think about then you have these oil droplets in water and they are covered with these surface active molecules. So they will at some point collide. So the oil droplets will come in contact with each other when they are in water. So these surface active molecules can also kind of form a mechanical or steric or electrical barrier between the drops. So then we don't see that type of a coalescence happening if you have these particles that can kind of prevent or molecules that can prevent this coalescence from happening. So that's another way how these molecules can stabilize emulsions. So they can prevent or at least make it, let's say, hinder the coalescence of emulsions.
Okay, so if you were describing that if you mixed oil and water and then after some time you would have like oil on top of water. Yeah. So basically what happens then is that all those oil bubbles, when they meet, they will combine into one. Exactly. And then they make the next one and then... Yes. Exactly. And now they can meet and nothing will really happen.
Yes, right. Exactly. Yeah.
Okay. So I was thinking about mayonnaise. I know that there is something called lecithin in egg yolk. Yeah. And I guess this is then a surface active molecule, an emulsifier in this case.
Yes, exactly.
Allows this to be mixed with the egg and the oil.
Yeah, exactly. And phospholipids and proteins are very common emulsifiers in food. But I mean, even particles can be emulsifiers. So these type of emulsions are called Pickering emulsions. Mm-hmm. Then, of course, the mechanism how they work is slightly different because you don't have that hydrophobic and hydrophilic part in the same way as you would in a phospholipid, for example. Then, I mean, in oil industry, for example, we have very stable emulsions that are formed between water and oil because we have these ingredients called asphaltenes in crude oil that can stabilize emulsions and make them really, really strong. And in this case, we of course need something to maybe break the emulsions.
Okay, right. So you have to get rid of that.
Exactly.
Interface stabilizing molecule.
Yes, exactly.
Somehow.
Yeah, exactly.
Okay. So can you measure this stability?
Yeah, to some extent. I mean, not directly, but interfacial rheology measurements can give us kind of indications or predict how the emulsion stability. So we have a few different ways of doing this. First of all, we can divide the interfacial rheology into two. So we have shear interfacial rheology, and then we have dilatational interfacial rheology. And the difference between the two is that in shear, we are actually just deforming the shape of the interface, basically, but not really increasing the area, whereas in dilatational, we are increasing the surface area. So one of the shear methods is called ISR, so it's interfacial shear rheometer, where we have a magnetic needle that is oscillated at the interface and with the help of a magnetic field. And then we are actually looking at that needle with the camera and measuring how much the needle is able to move at the interface with a certain magnetic field. This enables very sensitive measurements for interfacial properties. But I would maybe say that shear methods are not maybe, they are used maybe for more fundamental research, I would say, because it's a dilatational method, the setup of measurement is much more simple. So also we have a stronger indication that the dilatational interfacial rheological properties, and especially the interfacial, the elasticity of the surface, is something that can be linked to emulsion stability. So in dilatational methods, we are fluctuating, as I said, we are actually changing the interfacial area. And there are two ways to do it. One is with oscillating barriers. So you can have your let's say your interfacial layer on top of or in between oil and water, or on top of water. Then you oscillate it with the barrier. So you are actually increasing the surface area and decreasing the surface area. And at the same time, you're measuring the surface tension of changes at the interface. And this is also the other method that is very commonly used, which is called pulsating drop, is based on exactly the same method. So there we make a pendant drop. So we have talked about pendant drop before. So there we basically make a pendant drop which could be used to measure surface tension. But instead of just having it hang there statically, we are actually pulsating the drop with the known frequency. And then at the same time, we are measuring the surface or interfacial tension. And what we get is basically a sinusoidal curve, or two sinusoidal curves. One is for surface area, so that will change as a function of frequency. And then also we will get a sinusoidal curve for surface tension, which will be the same sinusoidal, with the same frequency. Then we are looking at these two curves. If they are in the same phase, then we are saying that the interface is completely elastic. If they are in a separate phase, then we can define the surface elastic and viscous component for that interface. And then, of course, this is automatically done by software. This information of surface tension as a function of frequency is basically used to calculate these elastic and viscous components for that interface.
So if you would do this on like a real emulsion, you would create like a model system, or could you actually do it on a real? Could you do it on mayonnaise, for example?
No, exactly. So that's actually a really good question, because it's no, you shouldn't take mayonnaise and start pulsating that, because it doesn't really tell you anything. You actually have to separate it into two components. So you would have your water and oil and whatever is the emulsifier that you use, which is in case of mayonnaise, it's the egg yolk that you are using to stabilize it. So you would typically create more like a model system, so that you have a oil, water, and then your emulsifier, and then you are looking at that.
And then also what you said with the oil, where you have an interface that you don't want to be stabilized, I guess you could then have that interface that you know is now stabilized, and then figure out how to break it.
Yeah, exactly. I mean, you could probably even do it so that you would then add different kind of demulsifying, so emulsion breaking components into your mixture, and you could look how the interface behaves if you add different components to break the emulsion. So yeah, that's
what could be an emulsion breaking component? Is that just something that interacts with that specific molecule? Or?
Yeah, exactly. It's something that is basically able to adsorb in between those surface active molecules that you have. Yeah. And then kind of separate them and break the emulsion in that way. Yeah, exactly.
Okay. So I was also thinking, you mentioned these two categories of measurements, the shear approach and the dilatational?
Yes, exactly.
Do they measure the same thing, or?
I mean, in a sense, yes, they are measuring the surface kind of interface, so rheological properties of the surface. And you are measuring basically elasticity and viscosity of the surface. But you always have to mention if it's a shear or if it's a dilatational method, because they do vary a bit, because you do have a different way of deforming the surface. So I think it's maybe easiest to understand if you think about the dilatational method, where you are actually increasing the surface area. So you are also allowing components from the bulk of the liquid to adsorb on the surface, or then they can desorb from the interface when you are decreasing the area. So you have also that kind of a mechanisms or phenomena going on at the interface. Whereas with the shear methods, it's, at least in theory, it's more controlled, because then you don't have that exchange between the bulk and the interface, because you are not really changing the size of the interface.
Okay, I see. Okay, so why is it important to measure this then? Or
there are so many examples where all kinds of products are some sort of emulsions. We have been talking about food products like mayonnaise, all sorts of pharmaceuticals or cosmetics, like a day cream is an emulsion. And of course, when you are manufacturing those emulsions, you want to be able to, for example, give some kind of a shelf lifetime for that product. If the stability of the emulsion is really bad, you can also only store it for a week, and then you see the separation happening. So it's very, very important that you have those stable emulsions in many cases. But also the other aspect that we have kind of touched upon is this breaking of emulsions. So there are also, like in oil industry and other processes as well, there are in industrial processes where you have oil and water in a process in some shape or form. What could happen is that you could accidentally produce these emulsions. And in oil industry, when you basically, in a sense, accidentally produce oil water emulsions because you are using water to get the oil out from the reservoir. So then what will happen is that you will form that emulsion, but you will also need to have a way to separate that water from oil. Otherwise, your oil is kind of a not so good quality oil if it contains a lot of water. So there are so many different industrial areas where this is very meaningful.
So research on this only?
I mean, there is a lot of research going on, but now we have started to also see that this could be may be used also in quality control purposes in some cases, so that you could kind of quickly check if the quality of your systems. So there are a lot of things, and the research is moving forward. I mean, this is barely, so it's there is a lot of research ongoing, and progress is for sure happening all the time on this.
Okay. Wow, so much information.
Yeah, I know. This is a pretty heavy topic.
Yeah, and so much terminology as well. So can you summarize this somehow, like the key information?
Sure. So I think maybe, I mean, this has certainly been just an introduction to this field, and very short introduction. And but I mean, I think the kind of the take-home messages are that, I mean, emulsions are everywhere, and the stability of them can be either wanted or unwanted. And this interfacial layer between the two phases that form the emulsion is very, very important if we think about the stability of the emulsion. And then measuring the interfacial rheological properties, and I would say especially measuring the dilatational elasticity of that interface, is something that can help you to predict if this interface or emulsion is stable or not. And this is a relatively simple measurement to make.
Okay, so a great introduction to this topic then. Thank you for sharing your knowledge.
Thank you very much.
And thank you for listening to this episode with me, Malin Edvardsson, and Susanna Lauren from Biolin Scientific. I would also like to take the opportunity to mention to those of you who are listening or watching that if you are interested in surface science or related topics, you should check out our blog, the Surface Science blog. Thank you.